Next topic for review is the complex number system. This could be something that some of you saw in your algebra class in the past, and there may be a handful of you to whom this is brand new. I like to teach it as though it is a brand new topic so I can introduce you to the complex number system properly. Essentially, the complex number system is defined to allow you to take the square root of negative numbers. It's defined on this basis. The square root of -1, which up until you see complex numbers is usually defined as a non-real answer. Now that you're delving into the complex number system, the square root of -1 is defined as this lowercase italicized value I. Whenever you see I used in mathematics, it's hardly ever going to represent a variable. It'll always, most often always represent this complex number definition, the square root of -1. Now if you take this equation and you square both sides of it, the left-hand side becomes I squared, the right-hand side becomes -1. So a very important extension of this same definition tells you that I is the only number you can square and get a negative result. So the imaginary number I is defined to be the only number that can be squared to give you that negative result. So just a quick, for instance, when you're dealing with square roots, you like to be able to simplify square roots whenever they can be simplified. Like some of them are pretty straightforward. The square root of 36, 36 is already a perfect square, and that just becomes +6. The way the complex number system works is if you're prompted to take the square root of -36, because of this definition right here, what you do is you realize, well, 36 is a perfect square, but the negative there means this is going to be a complex number or an imaginary number. So technically what happens is anytime you're prompted to take the square root of something negative, you'd go ahead and take the square root of the number as usual, which would be 6, but if there's a negative under the radical as well, that also prompts you to put an I with the answer. So the square root of -36 is 6I. Just an extra thing to have to commit to memory whenever you're dealing with a complex number system. So the anatomy of a complex number is this. You'll most often come across two parts to a complex number, a real part and an imaginary part. For example, here's a complex number involved in this next problem, 4 plus 7i. 4 is the real part, 7i is the imaginary part. So a purely complex number does have both parts to them. So whenever you're dealing with arithmetic on complex numbers, addition and subtraction is probably the easiest of the operations to deal with because it only falls back on combining like terms. So here you're prompted to take 3 complex numbers and then simplify this addition and subtraction calculation. Well, if your algebraic intuition kind of kicks in, all you really need to do is to remove the parentheses and identify the like terms. So the first pair of parentheses here, that pair is redundant. You don't have to do any sign changes, so you can just leave that as 4 plus 7i. The next pair of parentheses has a negative in front of it, so I'm subtracting this complex number, which gives you a proper sign change when the parentheses are removed. -8 and then minus -5i is plus 5i. And then the last pair is being added, so both parts of the complex number there are negative, so when those parentheses are removed, they'll keep their negative signs, -3 minus 9i. Now, all that falls back on doing to simplify this is just to combine your like terms. You've got a +4, a -8, and a -3. So if you combine all the real parts together, 4 minus 8 is -4, minus 3 more is going to be -7. And then you've got the other set of like terms of the complex numbers, +7i, +5i, and -9i. If you combine those together correctly, 7i plus 5i is 12i, and then 12i minus 9i is plus 3i. So addition and subtraction is relatively straightforward. All you need to do is identify and combine like terms. Okay. Now, multiplication is our next thing we're going to venture into. Multiplication is going to require you to remember this particular definition right here. Anytime you see an I raised to a power, you need to fall back on the fact that I squared equals -1 to help you simplify it down for your calculation. So when multiplying, I've got a reminder there to make sure you're aware that you'll need this property whenever you're dealing with multiplication of complex numbers. So the first problem here, there's actually, I guess, an example A and an example B. These are two separate examples I wanted to show you. Example A here is a couple of complex numbers being multiplied. And I'd like to think the algebraic intuition is pretty obvious here as well. You're really just doing a binomial times a binomial, so you'll want to use FOIL to multiply those together. So if you apply FOIL correctly, just thinking of it as two regular algebraic binomials being multiplied, first times first is going to give you 32. Outer times outer, positive 4 times negative 5i. Just think of it like a variable for a moment. We'll get into the definition of what I means later when we see the I square show up. But for now, you can just think of it as a variable. 4 times negative 5i is going to be negative 20i. For the I part of correction, for the O part of FOIL. The I part of FOIL, positive 7i times positive 8 will be plus 56i. And then finally, last times last, 7i times negative 5i is going to give you negative 35i squared. So yeah, it's perfectly fine to think of I almost as a variable while you're doing the first part of the calculation, but anytime you see a power of I show up in your calculation, you need to fall back on using this definition to simplify it thoroughly. So you've got a couple of like terms here in the middle. Same as always, it's almost always the case that the O and the I in FOIL are like terms. You can combine those readily. So 32, and then negative 20i plus 56i becomes plus 36i. And now here's where the definition kicks in. This last term is subtracted currently, but you're subtracting something that has an I squared in it. Anytime you see I squared, that gets immediately recalculated as negative 1. So this is technically minus 35 times a negative 1 when you apply that definition correctly. And so therefore the thing to remember is anytime you see an I squared on a term in a calculation, that's actually going to cause a proper sign change. So you're now dealing with 32 plus 36i plus 35. That's worthwhile committing to memory, is the I squared just changes the sign of the term that it's with, in this case from minus eventually to plus. And notice it now just becomes a real number, positive 35. That can be combined with the 32 in the front. So when all is said and done, the final answer for this calculation will be 67 plus 36i. Okay. Separate example here. I've got a couple of monomial complex numbers to raise to these powers. So the thing to remember in this case is just your properties of exponents. So if you're raising a monomial to a power here, you're going to have to cube the 3 and you have to cube the I to remove the parentheses. That's raising a monomial to a power. And here you're raising negative I to the 4th power. Well, whether it's imaginary or real or not, if you have a negative value raised to an even power, that's always going to turn positive. So to remove these parentheses, the negative is going to go away because of the even exponent, and then you'll have to properly deal with I to the 4th. So first part of simplifying this, the real coefficient is going to be 27, and then you're multiplying times I to the 7th power. So see, initially thinking of I as a variable, you can use properties like properties of exponents or foiling to get the first part of the calculation done. But you'll always need to remember that anytime a power of I shows up in your calculation, you got to fall back on that definition to help you simplify it as thoroughly as you can. So this is I to the 7th, and the definition only relates to I squared. So one way to deal with that is to take that I to the 7th and write it as an I squared times an I squared times an I squared times an I. You see, you can extend all these extra I squares out, and notice if you add all the exponents, 2 plus 2 plus 2 plus 1, it's still I to the 7th. But the reason I'm writing it this way is so I can use that definition and simplify this a little better. So this turns out to be 27 times negative 1 times negative 1 times negative 1 times I. And then when you multiply all those negative ones together, that's an odd number of negatives multiplied. So that's going to make your coefficient negative 27, and then with an I on the end. So whenever you're dealing with any kind of multiplication or powers of complex numbers, the highest power of I you should ever see at the end of your calculation would be I to the first. Now sometimes the I may go away. You may have a real number resulting. In that case, I just doesn't show up in your answer. But you shouldn't leave calculations involving like I raised to a power in your final answer, because you've got to extend your knowledge to this definition to make sure you can completely simplify it correctly. Okay? Well, next up is division with complex numbers. I'm going to go ahead and stop this first video, and then we'll kick into this division problem next, because division's probably the more lengthy calculation that you have to do with complex number arithmetic.